Today we are going to discuss wire-wound variable resistor, thermistor, electromotive force, source of EMF, internal resistance of a supply, terminal potential difference, electric power, and maximum power output. Wire-wound resistor. Special resistance wire is wrapped around an insulating core, typically porcelain, cement, or pressed paper. Normally, nickel chromium is used because they have low temperature coefficient. Low temperature coefficient means they can operate at higher temperatures safely. So they have high stability and accuracy. These resistors are typically used for high current applications with low resistance and appreciable power. Wire-wound resistors can be used in two ways: rheostat and potential divider. Rheostats are variable resistors. A variable resistor is a resistor whose resistance value can be changed. Here in this figure, representation of variable resistor is shown with two terminals. This is used in circuit diagrams. Rheostat is a resistor that controls current. Rheostat is variable resistance used to vary the amount of current or voltage in a circuit. Rheostat has two terminals. It is connected in series with the load and the voltage source. Rheostat varies the current. This figure shows the rheostat, internal structure of rheostat. One fixed contact of rheostat is connected to the circuit, and wiping contact, that is sliding contact, is also connected to a circuit. In this figure of rheostat, there are two terminals, terminal A and terminal B, and there is one sliding contact or wiper. Terminal A and this wiper are connected to the circuit. If we use the terminals A and B in the rheostat, the minimum resistance is achieved when we move the slider or wiper close to the terminal A, because the length of the resistive path decreases, and we know that resistance depends upon the length, so due to reduction in length, resistance also decreases. As a result, only a small amount of electric current is blocked and large amount of electric current is allowed. Due to decrease in resistance, large amount of current can flow. Similarly, if we move wiper away from terminal A, length of the resistive path increases, and due to increase in length, resistance will increase. In this condition, a small amount of current will flow. So by using rheostat, we can control the current. Wire wound resistors can be used as potential divider. From name you can understand that potential divider divides the potential. By the help of potential divider, we can divide the potential to get required voltage. A potential divider provides a convenient way of getting a variable potential difference from a fixed potential difference. With the help of a battery, a potential difference V is applied across the ends of A and B of the resistor. Let R be the resistance of wire AB. The current I passing through it will be I is equals to V upon R. In this circuit, wire is having resistance R and potential difference is applied across the ends of A and B of the resistor. Current flowing through this circuit is I is equals to V upon R. If RBC is the resistance between point B and C and I is the current between them, then the potential difference between B and C is VB to C is equals to IRB to C. Actually, we are not taking the whole resistance R. We are taking resistance from point B to C, and we know that current remains same in series combination. So we can write the potential difference across point B to C. VB to C is equals to IRB to C. R is resistance from point B to point C. I is current. current remains same, and VB to C is potential difference across point B to C. Putting the value of I is equals to V upon R, we get VB to C is equals to V upon R into RB to C. Hence, the potential difference across point B to C, VB to C is equals to RB to C divided by R into V. Value of RBC divided by R may vary due to the position of sliding contact C. When we move sliding contact C towards B, length of the resistance decreases, so we get smaller value of resistance, and when we move sliding contact towards A, length increases, hence we get larger value of resistance. Thermistor. Thermistor is combination of two words, thermal and resistor. Thermistors are temperature sensitive resistors whose resistance value changes with change in operating temperature. It is used in electronic circuits where temperature measurement, control, and compensation are desired. The temperature coefficient of a thermistor can be both positive and negative. Temperature coefficient is positive when with increase in temperature resistance increases, and temperature coefficient is when with increase in temperature resistance decreases. Application of thermistor. Thermistors are used in mobile phones, computers, LCD displays, CPUs, rechargeable batteries, and medical and patient monitoring equipment are all equipped with thermistors. Transformers, generators, washing machines, etc. AC, refrigerators, freezers, ovens, irons, and toasters. Thermistor is used in circuit with increase in temperature of a device connected with thermistor. Resistance of thermistor decreases due to negative temperature coefficient, so it allows more current to flow. Electromotive force. For running this CD player, energy is taken from the battery. Typical batteries and the symbol used to represent them in electric circuit. There are two terminals in the battery, positive terminal and negative terminal. Their symbol is shown with two parallel lines. One line indicates positive terminal and another line indicates negative terminal of the battery. Electromotive force, EMF. The energy needed to run a CD player, for instance, comes from the batteries. Within a battery, a chemical reaction occurs that transfers electrons from one terminal to another terminal. Because of the positive and negative charges on the battery terminals, an electric potential difference exists between them. The maximum potential difference is called the electromotive force EMF of the battery. The electric potential difference is also known as the voltage. So, in this battery, due to chemical reactions, electrons move from one terminal to another terminal. One terminal is positive charged and another terminal of this battery is negatively charged. Due to this positively charged terminal and negatively charged terminal, potential difference is created between these two terminals of the battery. That is known as EMF, electromotive force. The maximum electric potential difference that can exist between the terminals of the voltage source is called the electromotive force of that source. Electromotive force is defined as the work done in carrying 1 coulomb of charge through the source. Mathematically, EMF is equal to work done per unit charge. Its unit is 1 volt, that is equal to 1 joules per coulomb. Source of electromotive force. A device that, by doing work on charge, maintains a potential difference between its terminal is called a source of electromotive force EMF, as we have discussed in previous slide. Other form of energy is converted into electricity in a source of electromotive force. Battery converts chemical energy into electrical energy. Electric generator converts mechanical energy into electrical energy. Solar cell converts electromagnetic radiation into electrical energy. This symbol shows the source of electromotive force. Comparison of EMF and potential difference. EMF is the maximum potential difference between the two electrodes of the cell when no current is drawn from the cell, when the circuit is open. Potential difference is the difference of potentials between any 2 points in a closed circuit. EMF is the independent of the resistance of the circuit. Potential difference is proportional to the resistance between the given points. The term EMF is used only for the source of EMF. Potential difference is measured between any 2 points of the circuit. In a closed circuit, we can measure potential difference between any 2 points. EMF is greater than the potential difference between any 2 points in a circuit. However, potential difference is greater than EMF when the cell is being charged. Internal resistance of a supply. Actually, internal resistance is the resistance inside the EMF source. It is the opposition offered by the electrolyte of the cell to the flow of electric current through it. So, when charges move from one terminal to another terminal of the EMF source, electrolyte of the cell oppose these charges to move from one terminal to another terminal of the EMF source. So, this opposition offered by electrolyte to the flow of electric current is known as internal resistance of a supply. Factors affecting internal resistance of a cell. Larger the separation between the electrodes of the cell, more the length of the electrolyte through which current has to flow, and consequently a higher value of internal resistance. Greater the conductivity of the electrolyte, lesser is the internal resistance of the cell, as the internal resistance depends on the nature of the electrolyte. The internal resistance of a cell is inversely proportional to the common area of the electrode dipping in the electrolyte. The internal resistance of a cell depends on the nature of the electrodes. In this circuit, this small r represents the internal resistance of EMF source, and this capital R is representing the resistance of a wire. Current I flows through this circuit, and it can be written as I is equals to E divided by R plus R. Relation between terminal potential difference and electromotive force. As we know that current flowing through the circuit I is equals to E divided by R plus R. By rearranging equation we get E is equals to IR plus I into small r. Let's say it equation number 1. As we know that IR is equals to V. V is terminal voltage, terminal potential difference. And we get E is equals to V plus IR. When there is no internal resistance in the EMF source, R is equals to 0. By putting R is equals to 0 in above equation, we get V is equals to E minus I into 0 and V is equals to E. In this condition, when internal resistance of the EMF source is 0, so terminal potential difference becomes equal to EMF. For closed circuit, V is equals to E minus IR. We know that for closed circuit, terminal potential difference is less than EMF, and for this condition we subtract with the term IR from EMF. For open circuit, current is equals to 0. By putting I is equals to 0, we get V is equals to E minus 0 into R. Finally, we get terminal potential difference is equals to EMF. Electric power. The rate at which work is done in an electric circuit is called electric power. Of course, work is done on moving a charge in electric circuit. Mathematically, power is equals to energy per unit time or work done per unit time. Since the electrical energy is charge times voltage, the above equation becomes P is equals to Q into V divided by T. Since the current is charge flow per unit time, Q divided by T, the above equation becomes P is equals to QV divided by T is equals to Q divided by T into V. Q divided by T is equals to I. So we get P is equals to I into V. Since V is equals to IR, the above equation can also be written as P is equals to I into V is equals to I square R. By putting the value of V is equals to IR, we get I square R. And by putting the value of I is equals to V upon R, we get P is equals to V square divided by R. SI unit of power is watt. Kilowatt hour. It is unit of energy or electrical energy or work. It is amount of energy obtained by a power of 1 kilowatt in 1 hour. So 1 kilowatt hour is equals to 1000 watt multiplied by 3600 seconds. And by multiplying both values we get 3.6 exponent 6 watt second. As we know that 1 watt is equals to 1 joules per 1 second. So 1 joules is equals to 1 watt into 1 second. So we can write watt second as joules. And 1 kilowatt hour is equals to 3.6 exponent 6 joules. Utility companies use the unit kilowatt hour to measure the electrical energy used by customers. 1 kilowatt hour kWh is the energy consumed for 1 hour at a power rate of 1 kilowatt. Maximum power output. In many places, in many devices, we want maximum power output. For example, in radio or TV transmitting systems, it is desired to transfer the maximum power possible from the transmitting medium to the antenna system. We want maximum power transfer from amplifier to speaker system. This can be gained by proper matching of load resistance R and source resistance small r. We know that power output in a circuit is equals to I into V, and that is equals to I square R. Putting the value of I is equals to E divided by R plus small r, we get power output is equals to E square R divided by R plus small r whole square. In denominator, we can use formula A plus B whole square to expand this term, and we get E square R divided by R square plus 2R into small r plus R square plus 2. So we have to subtract it. That's why we write minus 2R into R, because it will cancel the effect of added term 2R into small r. 2R into small r plus 2R into small r gives us 4R into small r, and remaining terms can be closed into formula A minus B whole square, and we get R minus R whole square plus 4R into small r, and power output is equals to E square R divided by R minus small r whole square plus 4 capital R into small r. This is the power output from a circuit connected with EMF source. For maximum power output, we match the internal resistance of the EMF source with the load resistance capital R. For small r is equals to capital R, we get power output is equals to E square R divided by 4R into capital R, because in above equation R minus R gives 0, or we may get power output is equals to E square R divided by 4R into capital R. R is cancelled by R, and finally we get power output is equals to E square divided by 4R, or power output is equal to E square divided by 4 into capital R. So it can be concluded that maximum power is delivered to a load resistor R when the internal resistance of the source of EMF is equal to the load resistance, also called maximum power transfer theorem.